Okay, today we're going to start our unit on nuclear physics. Nuclear physics is important in nuclear medicine, nuclear power, nuclear propulsion, and nuclear weapons. Today we're going to just look at the structure of the nucleus. Back in 7th grade you learned that the atom was made of protons, neutrons, and electrons, and you learned that the nucleus was made of the protons and the neutrons. You probably didn't get much farther than that. Then in 10th grade you learned that the electrons were not orbiting randomly, but they were in distinct shells. And all of chemistry was the desire for these outer shells to be full. So atoms either gained or lost electrons to have a full outer shell. We don't care about any of that in this unit. We're going to focus instead on the nucleus. Okay? So, first thing you should know about the nucleus is size-wise, the nucleus is very small compared to the size of the atom. If this was the nucleus, the electrons would be all the way at Coles Mill Road. It would be about 1 kilometer between the nucleus and the innermost electron. What that tells us is the atom is almost all empty space. The nucleus is just a small, dense section in the middle where almost all the matter resides, but most of the atom is empty space. We are only focusing on this nucleus. We're going to neglect the empty space around it, and we're going to neglect the electrons that are orbiting. The first thing you should know about the nucleus is the impossibility of it based on what you already know. We know that positive charges should repel other positive charges, so this nucleus should blow itself apart in just a few nanoseconds. The neutrons have no charge, so they have no hope of holding the protons in place. So if it's impossible to have nuclei, how is it that they exist? Well, in order to understand this, you have to understand the 4 fundamental forces in the universe. Last year you learned about a bunch of forces: tension, elastic, buoyancy, friction, normal. Realize that none of those are fundamental forces. For instance, the force of friction turns out to be dependent upon the electrical force. Buoyancy, we saw, was dependent upon gravity. The only fundamental forces you've learned about so far are the force of gravity and the electromagnetic force. Gravity acts between objects with mass, but the masses have to be incredibly large for us to notice gravity. We are not going to see 2 normal masses getting stuck together. Gravity is just too weak. However, the electrical force is very strong. How strong? Strong enough that if you just rub a balloon in your hair, you create enough charge that you could actually measure and feel the electrical force. So you got this strong repulsion and a tiny, tiny attraction. There is no way that gravity is going to be able to hold this nucleus together. So there must be other forces acting that we don't know about. And in fact, we didn't know about them until kind of recently. The first of these forces was discovered in the 1930s by a scientist from Japan. He got the Nobel Prize for his discovery, and what he discovered was the mathematical nature of this force and how it depends upon distance, how it varies with distance. And what he found is that there was a strong attractive force acting between these nuclear particles, but that it's extremely short range. So in small nuclei, this force is enough to stop the repulsion, because this force will act as an attractive force between all these nuclear particles. So this nuclear strong force attracts protons to protons, neutrons to neutrons, and neutrons to protons. It acts between all these nuclear particles. However, because it's short range, when the atoms get too big, even though this proton can repel this proton, they can't attract each other with the nuclear strong force anymore because they're too far apart. So the electrical force, even though it's weaker, will dominate because it acts over larger distances. In fact, the electrical force and the gravitational force stretch out forever. They get weaker with distance, but they don't disappear. And they get weaker in an inverse squared relationship. With this nuclear strong force, it gets weak really quick. Before you get to the other side of a large atom, the nuclear strong force is pretty much down to 0. So the nuclear strong force limits the size of the nucleus. I also want you to realize that protons and neutrons are not the final word. So there are actually smaller particles that make up the proton and the neutron. Those smaller particles are called quarks. It turns out that the proton is composed of 3 quarks and the neutron is composed of 3 quarks. With the proton, there are 2 up quarks and a down quark, and with the neutron, it's 2 down quarks and an up quark. All right? So nuclear particles like neutrons and protons are not the final word. They're composed of quarks. The quarks are held together with the nuclear strong force, and these quarks were discovered by a scientist from America back in the 1960s. He got the Nobel Prize for this, and it is one of the big important discoveries of the last 100 years. It turns out that there are actually 6 different kinds of quarks. Only 2 of them seem to be important for normal everyday matter, and they are the up quark and the down quark. As we saw, the proton was composed of 2 ups and 1 down. You'll notice the charge of the up is positive 2/3. So we have positive 2/3, positive 2/3, and then a down quark is negative 1/3. And when we put all that together, we get a net charge of the proton of positive 1. The neutron has 1 up, which is 2/3, and then a down, which is negative 1/3, and negative 1/3. And when you total up all the charge, the neutron comes out to have 0 net charge. Okay? But these guys are built out of quarks that have charge, they have mass, they have spin. I'm not worried too much about the rest of this chart. Just make sure you know the charge and the symbol for the up and the down quarks. These other quarks, the charm and the strange, the top and the bottom, you'll notice they have the same charges as the up and the down quark, but they are much more massive, and they are not involved in the creation of everyday matter. And we are not sure how these quarks actually factor into the creation and maintenance of our universe. Okay? So focus mainly on the up and down quarks and what their charges are. We learn about these quarks and their properties in things like the Large Hadron Collider, which is a giant particle accelerator and particle collider. It's a large hadron. A hadron is any particle built out of quarks. So that would be things like our proton and our neutron. Okay? And when we look at a nucleus, here we have a nucleus with a proton, a neutron, another neutron, and a proton. And realize that each particle is made of quarks. The quarks are held together with the nuclear strong force, and then the nuclear strong force binds the nucleus together. So we got the nuclear strong force all over the place, holding this whole thing together. This would be an example of helium. It's got 2 protons and 2 neutrons. So specifically, it's a specific isotope of helium. This would be called helium-4. Why 4? Because it's got 4 particles in its nucleus. 2 protons, 2 neutrons. As you know, the important thing is the number of protons. Anytime you have 2 protons in the nucleus, it's helium. The neutrons are not as important, so you could have a version of helium that is 2 protons and 1 neutron, and that would be called helium-3. That's a different isotope of helium. Okay, we got a bunch of terms, and I just want to make sure that you are familiar with these. Some of them you've heard today, some of them you heard in chemistry, some of them you might have heard back in 7th grade. So we have fundamental particles. Fundamental particles are particles that are not made of simpler particles. So for instance, an electron is a fundamental particle. A proton is not. A proton is made up of other things, quarks as we saw. Quarks, these are the building blocks of the nucleus. Those are the things that actually create protons and neutrons. A hadron is anything that is built from quarks. So again, a proton and neutron would be an example of hadrons. We could have fancier hadrons that are built out of like those top and bottom quarks. We have no idea what to do with any of this stuff or how to keep it around. It doesn't even stay around in our universe long. But a hadron just refers to any particle built from quarks. The nucleus, as you know, is the center of the atom. Nucleons are particles that build the nucleus, so they would be your protons and your neutrons. Collectively, they're called nucleons. So when we had helium-4, it had 2 protons, 2 neutrons, which gives you 4 nucleons. 4 particles that made up the nucleus. Doesn't matter what they are when you're saying nucleon. It's just the total number of particles in there. Orbitals, we saw that's where the electrons were. That's not really too important for us. Ions, you learned that in chemistry class. Ion is an atom that has gained or lost electrons. Again, not too important for us. Isotopes are very important, and that's when you had different forms of the same element. Helium-4, helium-3, and so on. They are known as 2 different isotopes of helium. Atomic number, that would be your number of protons. The atomic number of helium is always 2. The atomic number defines the element. Mass number, that tells you the total number of particles, so it's kind of like nucleons. The atomic mass is the mass of one specific isotope. Atomic weight is the average mass of all the isotopes for a specific element. Okay, so I know I went through them pretty quick. If you didn't catch on to them, you will as we work through. Pause if any of them were too quick for you to write down. I just want to take a minute to make sure you understood the difference. So when we are looking at mass number for hydrogen here, again, that's how many particles. 2, 3, 4, 6, 10. How many particles there are in that nucleus. This is the atomic mass. That's the actual mass of that form of hydrogen. On the periodic table, when you look at hydrogen, you get the average of all of the different isotopes. Okay, the weighted average of all the different isotopes. Since almost all the isotopes of hydrogen are hydrogen 1, the average is very close to the atomic mass of hydrogen 1. Okay? These masses are given in something called atomic mass units. You might have learned in chemistry they're abbreviated AMU. 1 AMU is about 1.66 e to the negative 27 kilograms. Okay, so again, atomic mass is the mass of one specific isotope. Atomic weight is what you find on the periodic table, and that is more like the average. So if you notice lithium, lithium has an average of around 6.94, but when you look at lithium, there is none at 6.94. But if you were to average these two, weighting this one at 92.8% and this one at 7.5%, you would get your atomic weight. So the actual mass is the atomic mass and the weighted average, that's what we call atomic weight. I know this was a lot, but I wanted to get through these basics quickly so that we can get on to more advanced things. If you have any questions, ask me during McCullough.